This episode answers a simple question with a perhaps non-intuitive answer. Why does electricity matter so much in space? Space isn't governed by gravity alone. Above Earth's atmosphere, electric and magnetic fields dominate how particles move, how energy is stored, and how the region organizes itself. This is important because every satellite, every rocket, every astronaut that we send to space has to operate inside of this highly electric environment. In this episode, we're going to explore why space behaves this way, and why the rules that you're used to here on Earth stop applying once you go high enough.
Up to this point, we've established two things. First, space is not empty. It contains particles and fields. Second, Earth sits inside of a continuous outflow from the Sun, made of its charged particles and magnetic fields. The missing piece is how those particles behave.
If you'd like to watch either of the episodes on these topics, check the description below for links.
On Earth, most matter exists as solids, liquids, or neutral gases. In those states, atoms are electrically balanced. Positive charges and negative charges are bound together, and large-scale electric effects mostly cancel out. But in space, energy is high and collisions are rare. Atoms are frequently stripped apart into charged components, free electrons and ions. Once that happens, the material is no longer a neutral gas. It becomes what we call a plasma.
Plasma is a charged state of matter where electric and magnetic forces can control the motion and energy storage of particles better than pressure or gravity forces.
If space were mostly neutral gas, particles would move independently and almost nothing would ever be able to interact. But because space is filled with plasma, particles will behave collectively. They respond to fields, they generate currents, and they reorganize energy across enormous distances.
Start with a single charged particle. An electron or an ion does not move through space freely like an uncharged particle. Because it's charged, it's influenced heavily by the presence of electric and magnetic fields.
Electric fields do one thing very simply. They accelerate charged particles. If an electric field exists, a charged particle will gain speed in it. This is how energy is transferred directly into particle motion. Magnetic fields behave a little bit differently. A magnetic field doesn't really speed a particle up or slow it down. Instead, it changes the particle's direction. And when a charged particle moves through a magnetic field, its path bends, and the result is a curved trajectory that becomes a spiral around the magnetic field line.
This spiral motion is not rare. It's the dominant way that charged particles move throughout space. Once a particle begins spiraling around a magnetic field line, it becomes guided by it. It becomes very easy for that particle to move along the field line in this spiraling motion, but without outside forces acting on it, it can't move from one line to the other. This is why I say we can think of magnetic field lines as rails. They don't push particles forward, but they do constrain how they're able to move.
Now remove collisions. In Earth's lower atmosphere, particles collide constantly. Those collisions randomize the particle's motion and quickly outweigh the influence of the electric and magnetic forces. Any charge separation is neutralized almost immediately by surrounding particles. In space, collisions are rare. Particles can travel thousands of kilometers without ever touching another particle. In that environment, electromagnetic forces dominate. Because collisions are rare, the spiral motion around magnetic field lines persists. This is how particles remain organized by fields for long periods of time. The longer the path length and the lower the collision rate, the stronger the magnetic influence tends to be.
This is how we space physicists determine the functional transition point between atmosphere and space. Below it, collisions dominate and matter behaves like air. Above it, fields dominate and matter behaves like a plasma. If this kind of information is interesting to you, then check the links below. I've made a guide called 10 Fundamental Concepts About Space. In it, I simply give you a little bit of intuition about things that didn't make sense to me as a kid growing up without a science background.
Now scale all of this up from one particle to many. Space is filled with enormous populations of charged particles moving together. When those particles move collectively, they create electric currents. Those currents generate magnetic fields, and the fields then act back on the particles that created them. This feedback loop replaces collisions as the organizing mechanism. Instead of particles interacting through direct contact, they interact through fields. Information about motion, density, and energy is transmitted through electromagnetic forces at very high speeds. This allows plasma to behave as a single system. If particles in one region are accelerated, currents intensify. If currents intensify, magnetic fields strengthen. If magnetic fields strengthen, particle motion elsewhere is redirected. It's interesting to note, particles don't need to touch for this to happen. It's why plasma supports waves. Disturbances propagate through fields rather than through physical contact. Imagine this like shaking out a bedsheet. When you flick it, a wave forms across the fabric of the sheet, and you can watch that wave physically flow away from you until it reaches the edge of the sheet. And in reality, it continues into the particles of air around you. You just can't see it with your naked eye. Similarly, energy can move across vast regions of space without matter flowing along with it. Plasma stores energy this way as well. When flowing plasma stretches or compresses a magnetic field, energy is stored in the field's configuration. It exists even if particle motion temporarily slows.
When the magnetic field configuration changes, then that stored energy gets released. Particles get accelerated and currents intensify, and this causes entire regions of space to become reorganized. Around Earth, this process is continuous.
The solar wind delivers plasma and magnetic fields to Earth. Earth's magnetic field resists that flow, forcing it to divert around the planet, and in doing so, the magnetic field is compressed on the day side and stretched into a long tail on the night side. That stretching stores energy in Earth's magnetic field. Later, when that energy is released, particles are injected into new regions and radiation levels change. This causes things like auroras and currents to intensify. It also makes for a more hostile environment for satellites, spacecraft, and astronauts.
None of this would be possible in a neutral gas, and none of it would occur in empty space. It only happens because space is filled with plasma, and because that plasma is governed by collective electromagnetic behavior.
Once space becomes plasma, everything we place into orbit becomes electrically coupled to its environment, whether we design for it or not. Satellites are not isolated objects flying through empty space. They are conductive structures. It means that the material that they're made of transfers energy through itself, and this is immersed in a flow of charged particles and magnetic fields coming from the sun. As a satellite orbits Earth, different surfaces are exposed to sunlight, to shadow, and to different particle flows. Each of those conditions affects how the electric charge builds up on that part of the spacecraft. Sunlit surfaces tend to lose electrons due to photons colliding into it and ejecting them from the material, a process known as the photoelectric effect, and this causes them to become positively charged. Shadowed surfaces tend to accumulate electrons from the surrounding plasma and therefore becomes more negatively charged. Over time, these charging effects create electric potential differences across the vehicle, and if the voltage differences become large enough, electrostatic discharge can occur. These discharges can produce electrical arcing and are a well-established operational risk. A discharge can flip bits in memory, upset onboard electronics, damage sensors, or permanently disable components. Spacecraft are carefully grounded, coded, and electrically bonded or isolated in specific ways precisely because the space environment here is an electrified plasma. Radiation belts exist for the same reason. Charged particles can become trapped when Earth's magnetic field guides their motion. Once trapped along the field lines, those particles can circulate for long periods of time, repeatedly passing through the same regions of space. Satellites operating in or near these regions accumulate radiation damage slowly and predictably until conditions change.
When solar activity increases, particle populations grow and intensify, causing regions of space that were once survivable to become too hazardous. Mission planners account for this by limiting exposure time and adjusting orbits, while engineers account for it by continuously designing systems to better tolerate that increased exposure time. But none of this would be necessary if space were indeed electrically neutral.
Signals are affected in a more subtle but equally critical way. Radio waves and GPS signals do not travel through a vacuum. They propagate through plasma. Plasma has electrical properties that affect wave speed and direction. When plasma density changes, the signal's travel time changes as well. And when Earth's magnetic field configuration shifts, so do the paths that the signals travel along. For GPS, timing errors are everything. Position accuracy depends on measuring signal travel time to within nanoseconds, and small delays introduce significant position errors.
When plasma conditions are disturbed, these errors grow. Put simply, space weather causes GPS accuracy to degrade. It affects navigation, synchronization, and any process that depends on precise timing. Coordinating financial transactions, power grid consumptions, aviation navigation, all of these rely on space-based signals passing through an environment that's variable and charged.
Astronauts experience these consequences even more directly. Radiation exposure is not steady. It depends on plasma conditions around Earth. And during periods of heightened activity, energetic particle fluxes increase rapidly. In other words, many high-energy particles get crammed into the same space really fast. Shielding helps this, but it's not sufficient on its own. Spacewalks are planned during normal plasma conditions, but space weather is highly variable and often very difficult to predict. Therefore, exposure is actively managed. Human presence in space only works because, by default, we treat the environment as electrically and radiatively hostile, but these plasma-driven effects also reach us here on the ground. When strong currents flow in near-Earth space, they can induce currents in technology embedded in the surface of Earth itself. Long conductors such as power lines, pipelines, and underground cables will respond electrically. The surge of energy in their systems can saturate transformers and ideally trigger protective relays. But in extreme cases, the infrastructure fails. These failures are not driven by mechanical stress. They're the result of electromagnetic coupling between space and Earth. This is energy that's injected into near-Earth plasma populations, coupling with ground-based technology and even certain conductive geological structures through time-varying magnetic fields.
All of these consequences point back to the same physical reality. Space is not empty, nor is it neutral. It's an active electrical system that's made up of plasma, magnetic fields, and electric fields. And because it's electrical, that transition from air into space is not a fixed point. Air doesn't suddenly just become plasma. What really happens is that as particles go higher, they collide less often because there's more space between them. When those collisions become rare, electric fields have an easier time of accelerating those particles, and magnetic fields can then begin to steer them. This doesn't happen at a static line in the sky. The behavior changes over a range of conditions, which means that the question of where space begins isn't really about height, it's actually about particle behavior. That transition defines the real boundary, and that's where we're going to go next.
Thanks for hanging out. Make sure you subscribe, hit the like button. We'll see you next time.